Now, let's talk about rule induction. Rule induction is similar to structure induction, but the main difference is this rule induction is applied to a structure of derivation tree or proof rather than the structure of a syntactic object. So here's the basic idea. Suppose that we have a system of inference rules consisting of two rules. The first is the space rule. So we have a judgment JB. Let's call it rule base. And we have another inference rule which has these judgments as premises and the conclusion JI. Let's call this rule induction. So in this system, we have two inference rules where this is an axiom. This is over the general form. And now we'd like to prove if some judgment J holds by applying these inference rules, then we'd like to show that another judgment of this form, P of J, holds. So this is another judgment that is parameterized over this judgment J. So here's an example. Let's say J is n net, which says n is a natural number. Then we could have P of J as either n is even or n is odd. So we start with a judgment, and then we obtain another judgment, which is parameterized over the first judgment here. So for instance, if we change this syntactic object into n prime, then this should change it to n prime, and this one should change to n prime as well. So that's what I mean by parameterization over this judgment J. Okay, now given this goal, how does the rule induction technique proceed? So here is how it works. So in order to show that this judgment, the P of J holds whenever J holds, we consider two cases. First, the base case, which comes from this one. We show that P of JB holds, where this JB comes from here. So from this JB, we have this one. So we prove P of JB holds. So this is basically the base case. And next, we consider this inductive case. We consider this inference rule, which is not an axiom. In this case, we introduce induction hypothesis. So from this judgment J1 in the premise, we assume P of J1. And from this judgment J2, we assume P of J2. And so on. And we have P of Jn, where Jn comes from here. So we assume that all these judgments hold. Then we show that P of Ji holds, where Ji comes from here. So these guys are basically induction hypothesis, and this is going to be conclusion. So to summarize, in order to prove a statement like this one, then given this set of inference rules, we prove first this statement, which corresponds to the base case, and then this statement, which deals with this inductive case. That's how rule induction works. Now let's see why this technique, why this rule induction works. The idea is that if we have proofs that these two statements are true, then we can convert any derivation tree proving J into a corresponding derivation tree that proves P of J. So we can convert this derivation tree to another one that proves P of J. So therefore, whenever you have a proof of J, like with this derivation tree, you can also produce a proof of this judgment P of J with this derivation tree. Why is this the case? To see why, notice that we can imagine that from the first statement, from this first statement, we can imagine that there is an inference rule of this form, P of JB. Because this statement says P of JB holds. And from this statement, we can imagine that there is another inference rule of this form. The premise consisting of Pj1, Pj2 through Pjn, and the conclusion is Pji. So this inference rule is not something special. It's just a transcription of this statement, reformulated as an inference rule. That's all. So we can imagine that there is another system of two inference rules with these two inference rules. Now, suppose that there is this derivation tree proving J, then in general, it might have these premises, and we have these sub-derivation trees. And then whenever you encounter P of JB, whenever you encounter an application of this inference rule, whenever you have an application of this inference rule, you replace it with this one. And similarly, whenever you have an application of this inference rule somewhere here, you replace it with this inference rule. Then, if you think about this transformation, that is, you apply this transformation. That is, if you apply this transformation, this one into this one, and this one into this inference rule. The idea is we apply this transformation systematically to every part of this derivation tree, then we obtain another derivation tree proving P of J. That is, we apply this transformation to every part of this derivation tree. Then you can rewrite everything into P of J1, P of Jn, and the conclusion is going to be P of J. So that's the idea. And that's why this rule induction works. The idea is you can transform a derivation tree proving judgment J into a corresponding derivation tree proving P of J from these two statements. So let's see a concrete example. Earlier, we considered two systems of inference rules for judgment and net, and two judgment and even and odd. So for this judgment, we have two inference rule. 0 is net, so this is 0 rule. And we also have this inference rule, and net leads to successor and net. This is the successor rule. And for these two judgments, we have three inference rules. First, 0 is even. This is 0 even rule. And we have the successor case. If n is odd, then successor n is even. This is a successor even rule. Finally, we have this inference rule. Successor n is odd if n is even. This is a successor odd rule. Now, given these two systems of inference rules, we'd like to prove this theorem. If n net holds, then either n even or n odd. So you can think of this judgment as J in the previous statement, and this one as P of J, another judgment that was derived from this judgment J. And the proof proceeds by rule induction, on judgment and net. So it's very important to learn that we are applying rule induction on the judgment and net, not to the syntactic object n here. That's the critical difference from structural induction that we learned earlier. In the case of a rule induction, we are applying induction to this judgment. To be precise, we are applying the induction on the structure of the proof of this judgment. What that means is that we assume that there is a proof of n net, like we have this derivation tree where the root is this judgment, and we are going to analyze the structure of this derivation tree. That's the essence of this rule induction. So some people prefer a different phrase. Instead of saying rule induction, they want to write by induction on the structure of the proof of and net. And this thing basically means the derivation tree. So these two statements are equivalent. You could either say by rule induction on the judgment and net, which is tantamount to saying by induction on the structure of the derivation tree of n net. So this statement is just a shorthand for this one, and the idea is the same. Basically, you want to analyze the structure of this derivation tree, not the structure of this syntactic object n. If you analyze the syntactic object n, the whole proof reverts to applying structural induction, not the rule induction. So let's proceed. Because we are going to analyze the structure of this derivation tree, we want to focus on the last inference rule applied in this derivation tree. Because there are two inference rules that deduce this judgment. So there are two inference rules that prove judgment of this form, this inference rule and this inference rule. If we analyze the structure of the derivation tree of this and that, there are two cases. The last inference rule here is either an application of this zero rule, or the last inference rule applied here could be this successor rule. So note that we are analyzing the structure of this derivation tree, not the structure of this syntactic object n. As I said before, that's the critical difference. So we are going to have two cases. So the first case is the case where the last inference rule in this derivation tree is the application of the rule 0. So now you compare this derivation tree against this inference rule. Then we must have this equality. This n must be 0, the syntactic object 0. So the first can be written as 0 net has been proven by applying the inference rule 0. In this case, n net is basically 0 net. Or alternatively, we could say where n is equal to 0. This is symbol 0. So this is the first case. And so in this case, basically j is n net. And n is 0, so we have 0 net. So therefore, p of j is either 0 even or 0 odd. So this is what you want to prove. So whatever comes here should lead to the conclusion that we are expecting, which is either 0 even or 0 odd. And in this particular case, the proof is trivial because 0 is actually even. So we have a proof that 0 is even. So remember that the way that we present this formal proof is place the conclusion on the left side and then place the justification on the right side. So I'd like to say that 0 even holds. So this is the conclusion. And then what is the justification? The justification is by the rule 0 even. So I'm talking about this inference rule. So that's the style of the presentation that we'd like to see in these formal proofs. So now we have this proof, and then this one automatically implies this one because this statement is stronger than this one. So the first case is gone. The other case deals with the derivation tree of this form. So we have this derivation tree where the root of the derivation tree is n net. But now we are analyzing the structure of this derivation tree, and the last inference rule is actually this rule, successor rule. And then you compare the form of judgment here against the judgment shown over here. So perhaps we should introduce another meta variable. So this n net is actually successor n prime, where n is equal to successor n prime. So this time the derivation tree looks like this one, and the premise is n prime net. Now Now, so the case is this time successor n prime net, and the premise is n prime net, and the rule is a successor. So what is omitted here is this statement. The last inference rule in the derivation tree of n net is this rule successor. That's what is implied implicitly here. So this is the inductive case. Now we have J. J is basically successor n prime net, and P of J is basically either successor n prime even or successor n prime odd. So the conclusion, the final conclusion that we have to draw here is either successor n prime even or successor n prime odd, this one. And in this case, we have the induction hypothesis. And the reason that we can have an induction hypothesis is, remember that we are analyzing the structure of this derivation tree. Now, we have a smaller, strictly smaller derivation tree inside. So by applying something like a mathematical induction, you can introduce induction hypothesis from this smaller derivation tree. It's something smaller. So we can introduce an induction hypothesis here from this segment n prime net. Right, so let me erase this one. Right, so by induction hypothesis on the premise, which is n prime net, we can have either n prime even or n prime odd. So this is the induction hypothesis. Now, the remaining job is to somehow bridge the gap between this induction hypothesis and the final conclusion. So this is an easy exercise, but the point of the whole exercise here is not how this particular example works, but the way that we'd like to present the formal proof and how rule induction works. So let's complete the proof. If this is the case, let's just say assume, for example, n prime even. This is the assumption. Then we apply a successor even rule. We have successor even odd. This is by successor odd rule. So therefore, we have this one. This statement is strictly stronger than this one. And the other case is symmetric. So suppose that n prime odd from here, then this is assumption. Then by applying successor even, we can have successor n prime even. So whichever branch we take, we can always produce the desired goal, this one. So that's how rule induction proceeds. The key point here is rule induction analyzes the structure of this derivation tree. That's the key idea.